Welcome back, everyone. AK is here, and we are back on AK Academy after being off for more than 14 months. Here we are back again. I don't know how all this period has passed that quickly, but it did, and we are here anyway. I'm so happy to be back. Right now, I decided to having a new launch for this channel, the same level of the topic and the content and the technical stuff, but hopefully this time it's going to be way more consistent. Which is the goal that has always we all want, basically. So we always keep seeing new content. We don't interrupt courses or stuff like that. And for me, I stay engaged in the training, the preparation, the learning, and all those things. All right. So what do we have as the first session after this campaign? So it's just a good challenge I passed across in like the last couple of weeks. And I just would like to share the results with you. Basically, on the side during the weekends, I was building like a typing software, and it's a native Windows app. So this software is just like any other practice or touch typing software. This one does the same, but it does it like a little bit differently. It's native, so it leverages more performance from the client, so the typing experience feels more smooth. But it has some challenges that you can compete with other users globally. So whoever done a session, you can compete with him. So there was one request that started the session. I'm going to show you that in a bit. And I set a goal for myself. Regardless of the number of the users, regardless of the number of the sessions, you are going to be matched with a user that close to your speed in less than 1 millisecond. I don't want to see loading. I don't want the user to wait, not for even like a second or half a second. It should be instant to a level that I didn't add a loading progress on the client whenever you click start. So before we deep dive, let me show you the app very quick so you can get an idea of what I'm talking about. So here is the app. We just have a dashboard. We're not going to get into the deep details, but here is the feature. So whenever you click start, you need to get a text to type, and you will get another user or a competitor who did the exact same text and got a similar time to yours. So without loading, and it should be so fast that it feels local 100%. And if I click start, okay, I'll be asked to review. Sorry, this is my app. All right, so let's try again. So new session, new session, new session. So directly, you see, you get the text and you get a user who is close to my speed. My speed is 88, he's 84, but if I log in with a different account, you will get like a lower speed. There is around 1,500 sessions right now, which is quite a lot. So as you can see, already had Control N, no waiting completely. So I'm going to walk you through how this has been implemented on the back end and how this actually happened. So let me first talk to you through the why behind it. I always wanted the smoothest and most responsive user experience ever. That's why I went native on Windows. Like when the user wants to type, he keeps practicing without waiting, not even for a second. That was a very important thing. So I typed this goal before I even started the development of this feature. Keep the user in the practice flow with minimum to no distractions, not even with a waiting progress ring for a second. And I set the goal for 50 milliseconds, and then I found a way that it ended up being 1. And it can be less. That will depend on the server, actually. So before I start so quickly, let's talk about some concepts that we have in the app so that you are familiar with what we'll be talking about when showing the architecture. So we have 3 main entities. The user, which is actually basically the user who is typing. We have a user entity. You have a typing text, and the typing text is this. Whatever you see here, and it has some metadata, of course, for statistics. And there is a typing grace. Typing grace is the session that the user does. Like we have this text, this is my user, and I'll type this very quick. Okay, so I finished the session right now. I got 78 words per minute. And this is the time I got, this is the time compared to the competitor, and those are all the statistics. This object that represents this session I have done at this moment in time for this text called typing grace. So just to clarify those points. Now, To resolve this issue, it's not technically as much as it is domain knowledge. I built this app, I know like what each entity has and what each property does in this, and I use that capability to solve this issue and get to 1 millisecond. My understanding for the domain overall, like what's the typing text, what is arrays, how I can use them basically to come up with like a quick solution, or maybe data modeling that helps me with to build that scalable solution. So it's very important to always, whatever you are building, it's your app, business app, enterprise, demo, always make sure to have a good knowledge about the domain you are developing an app for. If in your company, always try to sit with the domain expertise, get their insights, and get to know more about what you are building and why you are building it. It's very, very important, and we are going to see in a bit how this helped me get that solution done. Now, regarding the tools, basically, I used Cosmos due to the nature of the schemaless nature of the data, and the app is ASP.NET Core hosted on Azure. Currently, it's on the development tier because I don't have so many users up to this moment, but I can scale. All right, let's go to a diagram right now and see how this solution is actually implemented. So it's going to be a little bit tricky, but I'll try to simplify it as much as possible. So here's what we have. The user wants to start a ranked session. I'm going to start from the end and then go back to the beginning. So what do we expect? We need the DTO that contains the text, contains arrays of other users. If I go to this app, here's another competitor. I have his race, his time, his speed, his details, and his reply of a race he done. So we can make those avatars race each other. So we need a race of a competitor and the competitor details so you can see who you are racing in here. This is the object, but this should be retrieved in 1 millisecond. Query all the database for all those races and get the closest one in 1 millisecond. So here is just a sample picture. This is the text, represents this green line. The typing rate represents the movement that the avatar is doing, or the competitor, which is a ghost feature, and the time. And the competitor is, his up-to-date details. All right, how the solution has been implemented. As you can see, each system writes and reads. This one writes races whenever we finish. I finish this race, it's linked right now to the server. But I also read sessions. Whenever I click new, I read. So I need to make a trade-off. Is it write heavy or write heavy? My app is read heavy. I don't care about the write. Let it take its time. It's happening in the background. But I want to optimize it for read, because when multiple users open and click a new session, it should be instant. I didn't like this text. I want another one. New. If there is loading, I have to wait. Users won't stay in the loop for long. Cool. So what is the solution I follow? Definitely I didn't went into querying the database and find the best one. That didn't happen. I found the solutions to storing and modeling, materializing the data in a way that it can be pitched directly without any prior querying stuff or querying during the request. So the storing first, it starts the moment we save the result. Then prepare a queue in the background, and lastly, do the retrieve, which all it does, bring an item from the queue. 1 millisecond, it's 01 from the algorithmic complexity. Cool, so how the data is stored then to get this solution? Let's go in here and start from whenever we finish a race. When the user finishes a race, we took all these details, the statistics, the numbers, the accuracy, the mistakes, all of those, and we create a typing race object. This typing race object is being submitted to the server, which is an API hosted an API service, Azure App Service, and our database is Cosmos DB. So what do we have inside it? If we go in here, initially, we have two containers, one named users and one named texts. The users container contains the profile of each user we have and all the races they do. So this the biggest container in the system. It might have, if we have like 10,000 users, each doing a race, 100 race, so that will be like 1 million record in addition to the race. So I use a discriminator to distinguish between a race and a user profile, and it's partitioned using user ID. Let's go to the database and see how this looks like. Here is users, and if I expand the items, I can see two types of documents. Click here, for example. You can see this is how user looks like. Metadata, email, profile picture, and so on, and the statistics. What is his total speed? What is his practice speed? His WPM, average speed, all this stuff. And the races that this user is doing. This is a race. And as you can see, it has the word speed, operations, which is character by character of what the user is doing, mistakes, session speed, rounding time, and so on. It's a little bit big object, so if we query this, order where c.user ID equals this user ID, you're going to find the user profile first, and then all the races this user has done. Great. Now, what is the other container? Is the text. Text simply hosts the catalog of those texts. It has a limited number of texts. It's like, in the worst case, there are 200 or 300. We add it gradually between one text or two. So it's just catalog of text. So if we go in here, we expand, it supports multiple languages. So we partition by language code. And you can see text, author, time and second, title, and so on. Nothing so crucial, something very simple. Great. So if I keep the data as is and just store it like that, which is nothing super up to this moment, and I want to get the ranked session, what would I do? I will start by querying a random text from the database. This is okay. It's not a big deal. 300 items, we can query one. Then I want for that text, let's say we got this text about electric cars. Now we need to go see all the users who, through all these races, their races that done this text specifically, and then fetch the closest one. So we might iterate over like 100,000 races. This is going to be very slow, very unscalable. More users, more races, this one gets slower and slower and slower until to reach a point it's impossible. If we have like thousands of users, it won't work. And in nature, it's slow. So what I did instead is, the moment we save the typing race, I create a new container named text traces. So I take the exact same copy of that trace and I store it in another container. But this container is instead partitioned by text ID, not by user ID. So this electric cars, we will have some races done for this. But why some races and not all the races being stored here? Let me show you what I'm doing. I have the speed, which is calculated in words per minute. This is a very important property, or the most important. So I normalize all the speeds into levels. Like from 0 to 1 is level 1. From 0 to 20, 10 to 20 is level 2. 60 to 70, level 6. And so on. So I divide them into 9 levels. And whatever race comes or being saved, I check what level is that race. It is like level, it's 100 WPM, so level 9. Okay, is there a text in level 9? No, then add it. If it's already a race, then update it. So always, for each text ID, because this one is partitioned by text ID, we will have maximum 10 races using that property. So now, after we fetch a random text, if we want to get the closest user, go search by the level, we iterate over 10 texts in the worst case, and we will get one. This solution, if there is like 1 million races, 10 million races, it will still give the exact same results. Notice again, I'm saving the exact same document, but in a different partitioning strategy, and I'm filtering through levels. Like I'm reducing the number of races to be stored. Instead of storing each one, I'm storing only the one race for each level. One race for the speed between 0 and 10, 30 to 40, and so on. Okay, that's great. But even though we don't do the processing directly, because I'm aiming for 1 millisecond. So if we want to do the query in the database, it will take more than that. Now we go to the coding part. That's how the data is stored. If you go to the database, you can see it here. Text traces, items. That's the same race object you have seen here. It's being copied, but it has a property named level. So levels are just ranges of speed. From to is a specific level. They are hard-coded in the code. You will see that in a moment. And you can see we query them by text ID. And worst case for each text, we will find between no to the maximum number of levels, which is 9 or 10. I don't remember exactly. Great. Now, in the background of our ASP.NET Core app, I have a service named Ranked Session Service. It's a Singleton service that runs on the background. Whenever the app starts, what it does is it goes and fetches all the texts we have. They are very limited catalog, fetches all of them, and then shuffle them. Just do some randomizing, only shuffling. The stage 2 starts. It only picks 10 out of those 200 or 300. This is an arbitrary number. I put it 10, but it can be anything. And right now I have 10 different texts. The next step is to go retrieve the races for each of those texts, but not from the user's container, because this will contain all the races done across all the system. I fetch them from the text races. So it's partitioned by typing text, and for each text we have limited number, between 1 to 10. So in the worst case, for 10 races, 10 texts, if all users done all those texts, we will get 100. Very small number. It doesn't even exceed the 2 kilobytes of data to stay in the memory. We fetch all the races. Now we have text, and it's typing races for all the levels, as you can see. Level 6, level 7, 3, 2, 9. Same for the number of texts we pick, which is 10. After that, we go fetch, for each race of those is being done by user. We fetch the users, a light version of the user basically, just the statistics. So we can populate this section here. The flag, the picture, the speed, just to keep the details up to date always. And right now we have this shape, list of text, and have a list of races with the up-to-date user information based on the last race they did. So all with the details you see here is live. Great. Last step, combine each of those into an object named queue item session and add all of them into a queue. Here is the queue. So now we have queue of 10 items. Each item is text and races of all the levels. And that's the final stage. All of this happening in the background. It's being done for all the users concurrently. It's not for each user. It doesn't have any effect on the thread or the request that the user is sending. Cool. Let's go right now to the beginning. The user clicked new session. What happens and how it's being fetched that fast? The request goes to the API. It sends the language and the speed of the current user in the query parameters. So My speed right now is 88, so I want a raise similar to 88 if there is any. If not, don't retrieve anything. And I'm looking for an English text, so there is other languages. So this one, the inbounds triggered, and all what it does, super simple. Go to the queue and fetch the first item. Cool. Now we get the first item. This is the text, which is, let's say, about Venice in Italy. And it has 5 different races from different levels for different users. Now, the speed here we are giving in an example is 64 words per minute, level 6. So give me the race closest to level 6, or level 6 if it's there already. And there is one. All right. So it takes this and it retrieves back to the client, and it adds a notification to the background service that, hey, race has been consumed, add a new one to the queue, a refill mechanism. So we go like that, and the user gets this data and they show. So when we click new, queue an item and dequeue, iterate over 5 items and retrieve the data. So in the algorithm complexity, it's 01, so fast, fully in memory, and item has dequeued, refill command has started, and right now new item has been added again to the queue. Great. Let's move to the code and see a little bit how this has been implemented. So this is the endpoint, this is the controller, this is the action in the controller, it's a GET request, and here we have a query. Start the query. It registered the service that named iRank session service, and what it has is, first it checks if it's empty, no items in the queue, then refill. Then that won't happen because this is happening at the beginning of the app, and with every race we add a new one, so this doesn't have a chance to be triggered unless something went wrong. Here is the process: race equals get next. So let's see, what does this one do? Here we have a concurrent queue for the language, and of course we check if there is anything wrong, empty stuff, and here we say try the queue an item. So take the first item from the queue and put it here. Now we have the text and all the races. We check, does it have any races? Like, is there other users who has done this race before? If not, okay, just retrieve the text. There is no competitor. If there is any, then what is the speed of the user? 88. So this is level. Let's go check the level. Okay, so those are the levels. 88, so it's level 5. So go and iterate over those races, all the levels, and try to find the one that's 5 or the closest to 5, like 4 or 7, 6. It depends, whatever is available. Take that race, return it to the client. So quick, so fast, so instant. This is a quick glimpse of the get next. It doesn't do any logic simply. But this is the generate and in-queue async. So let's repeat the steps of what it does very quickly. It fetch all the texts, shuffle them, pick 10 randomly, pick their text races, pick their users, populate them, and add them to the queue. Only that. So here we do exactly that. We check, we run a query against the database to get all the texts with some criteria, and I'll come back to this in a second. We execute the query, we retrieve all the texts we have, we shuffle them, and we cache them in the memory. We keep them in the memory for 20 minutes, so we don't every time go fetch them because they don't change a lot. And here we check at the beginning if they are cached in memory, retrieve them, otherwise execute the query. Cool. That's the first step. Then we pick randomly 10 of them. This code needs to be improved a little bit. We just take 10 out of this catalog, and we take the text IDs. There we go. We extract the text IDs, and we run a query against the text races to fetch all the races done for each text based on the labels. So this will get us, worst case, 100 items, because 10 items in the queue, we have, 7 levels, so worst case it will be 70 items. Then we take their user IDs, who done those races, and we fetch the users by their IDs. So we make sure that we have the up-to-date information about this user right now. So you know all about your competitor. Okay, we iterate over the races, we populate for each race the details of the user, just use WPM, profile picture, display name, and country code. And finally, we iterate over those texts. We create a new queue item. It has the text and all the text races. We just build this. We group them by text, text all the races, and add them to the queue. Now, the queue is populated, and when the user hits that endpoint, this getNext is called, and it retrieves that instantly, as we have token. So, this is the idea I would like to share. It was a quite interesting challenge, and I have tested that heavily. Even if there is like thousands of phrases, millions of phrases, it will still give the exact same performance due to this partitioning strategy that we currently use and the materialization or the normalization of the data based on those levels. But does this work? Like, if this is the right solution for every problem that requires to be that fast, or you want to retrieve it that way? It's not 100% the same, but if you have good understanding of your domain knowledge, if you have good understanding of your domain that you are developing for, you can get similar solution, maybe better. Because here I use the WPM to resolve the issue. Create levels, it's resolved. But you can do the same for other domains or other type of apps. The idea is to always have your head around the problem. You try to take advantage of all the data. It's not only about the tools. Sometimes it's the data, it's the knowledge, what you are trying to build that helps you solve such a problem. And we get this 1 millisecond. So if we check the requests, as you can see, the worst one is 1.1 millisecond. Or sorry, the average. If we check the min, it's half a millisecond. That's why it's so fast. So there is many other challenges I have gone through, and I'm trying to share all of those in separate videos. I hope you enjoyed this one and you get some information or ways to solve such problems using technologies, knowledge, and so on. And I hope you enjoyed the video overall. And if you don't, please don't forget to leave us a comment and hit the like, subscribe, so we can encourage us to keep going. Thank you so much, and talk to you.